All right, today we're going to talk about um, electron configurations and sizes and kind of delve in a little bit deeper about chemical bonding and some of those concepts. All right, now, and some of this you already did with Shakashiri, so hopefully it shouldn't be too much more information, but in most cases, atoms and compounds like to have noble gas configurations, right? That's what makes them happy. And in other words, they fill that p sublevel. Okay, so if they've got that p filled, they're happy. Now for nonmetals to do that, they will share electrons to make covalent bonds. They also can take electrons from metals to form anions. Nonmetals will do that by giving electrons to nonmetals to form cations. And this is really, it's not all the ways, but it's the most simple ways that can happen. Now, just to show you, these are some atoms that have multiple oxidation states or multiple ions. And we haven't thought of it this way, but the higher number electrons, these are all metals because they're all forming cations, the higher number where they've given away, like for example, this is where tin gave away 4 electrons, they had to lose both s and p electrons. Whereas the smaller numbers, they only have to give the p electrons away. And there are just some patterns that we see about more stability in terms of whether or not they leave those, but just to kind of point that out. And again, the trends are what is most important. A cation, this is for sizes. The cation is generally smaller than the parent atom, and that's simply because there's more protons. If you take an electron away, there's now more protons attracting those electrons in the atom. Um, and an anion will be larger. And it's not just that you're adding an electron and you're adding layer, it's that you're adding more electrons without adding additional protons. So there's more repulsion between those electrons, and that's going to cause it to get bigger. And these are things that we've seen, but these are common ions with noble gas configurations. You've got your group 1s, your lithium, your sodium, group 2s, aluminum 4 is a 3 plus, then you've got your oxides and your sulfides, and then your halogens, and they all have that shared common electron configuration. Now, for sizes of ions, a new term this year is when we talk about isoelectronic ions, and these are ions with the same number of electrons. So if you look back on the last slide, all of those ones that had back here for just a second, all of these right here have neons configuration, and that's what we're going to talk about. So whether it's the sodium ion, the magnesium, aluminum oxide, or fluoride, they all wanted to and did obtain neons electron configuration. So if you look at these, they all have the same number of protons, but they have, all have the same number of electrons because they all have neons configuration. They have different numbers of protons. So therefore we can compare them according to the size, and the electrons have a greater attraction to the nucleus as the number of protons increases. So here is the largest attraction. So the size will decrease as the nuclear charge increases, or its opposite order from above. Or in other words, your oxide ion is going to be the largest because it has the fewest number of protons trying to attract those to the center, whereas your aluminum 3 plus is going to be the smallest because it has the largest numbers of protons pulling those same electrons in. Okay, and this is just again showing you some comparisons of differences in sizes where you have, all of these have the same configuration. And aluminum, this is the actual radii on this slide, and these are all grouped in what's called isoelectronic. Iso means same, electronic refers to electrons. Excuse me. Okay, so write electron configurations for the most stable ion. And again, we kind of did this in shock, so I think we should be in good shape. But if you come back to this slide, it's just going on the idea that rubidium, again, is going to be a +1 because it wants to get that 4p6. It wants to give away that 5s1 electron. Okay, same with selenium. It's going to form 2 minus. It's going to gain 2 more to fill the 4p6. Iodine is going to be the same way. It's going to get that last 5p6 electron. Okay, so 3 ions that are isoelectronic with neon, place them in order of decreasing size. We kind of already did this, so that's why we have nitrogen as the first. We just added one here, where nitride would be the largest, aluminum would be the smallest. For each of the following groups, place atoms in the order of decreasing size. Again, we saw this a little bit last time. For the coppers, they all have 29 protons. So the lower the electron is going to mean or indicate the smaller the ion. So that's why we get this result here, because copper 2 has given away 2 electrons, so that's why it's going to be the smallest of the 3. Same thing with these. You have different amounts of electrons and energy levels, so that we would rank them this way. This should be protons as well. And so what we're looking at is the energy level to determine the difference between these. And then same thing, same number of protons, so more electrons means a larger ion. So that's why oxygen by itself is going to be the smallest, and oxide would be the largest. Okay, formation of a binary compound. We need to look at kind of the energy. Now, we talked about lattice energy last year. We defined it. Formal fancy definitions, the change in energy that takes place when separate gaseous ions come together to form an ionic solid. It always has a negative sign because it's an exothermic process. All right, and again, when they bond, they have lower potential energy. Okay, and that's a rationale of what we're trying to look at. Now, to add a little bit of math to that for this year, okay, this is an equation that calculates lattice energy. K is going to depend on the structure of the solid and the electron configurations, and then Q is your charges that you have, and the process will become more exothermic. And there are some examples of this in your textbook if you want to go look at them, as the ionic charges increase and as the distance between the ions decrease. And that's just mathematical relationships up here. If this is the charges, well, as there's a larger number, that's going to make sense that this is going to get bigger. And then the radius, the distance between those, that will also influence it. And K is usually given to us, so like I said, you can see those in the book. Okay, what we have to be able to do now is look at the energy, the total energy of the formation of an ionic solid. And again, I believe that there's a few differences on the PowerPoints that you have. The books, the page numbers in your PowerPoint are correct, page 362. But for the sublimation of solid metal, this is the delta H, it's just the energy of sublimation. Remember, sublimation is going directly from a solid to a gas. That's going to require the input of 161 kilojoules. Now, what we're trying to do is get the overall perspective of when we take lithium and fluorine and we form lithium fluoride. So this is one where the end result may make a little bit more sense here. Ionization of gaseous metals is the first ionization energy. First ionization energy of lithium, remember we're ripping off that electron, 520 kilojoules. It's going to take the input of that energy. Then we need to dissociate the nonmetal molecules, or the bond energy of fluorine. Now, just to show you where the 77 came from, and it says to look on page 362, the total bond energy of 2 fluorine molecules is 154 kilojoules. Well, to form 1 mole of lithium fluoride, which is what we're trying to do here, you only need 1/2 of that. So that's why we divide it in 2 and divide it by 77 kilojoules. Again, read the book here. It's going to give you a lot more detail in terms of what you need. Now, the formation of a nonmetal ion is the electron affinity piece. Electron affinity is adding an electron. So fluorine gains an electron. It's exothermic, so it's to be negative 328 kilojoules. And then finally, the last piece is the formation of the solid from the gaseous ions, which is the lattice energy. So it's really just going step by step in looking at the formation of lithium fluoride from the elements themselves. And then all we have to do is add up all of those numbers, and we get an overall energy of negative 617 kilojoules for the formation of lithium fluoride. And these would be numbers that would have to be given to you. You would just have to rearrange them correctly. And this is just showing you all the parts and pieces, right? Here you have, when you're adding things in, when you're splitting things apart, but ultimately the overall change is still negative 617 kilojoules. This is just giving you a perspective from the lattice energy piece. Okay, only difference here, this is going solid to gas, so there's your sublimation. Some of the parts and pieces that we just had here is splitting apart the fluorine, and then we start to get into the changing the fluorine from a neutral atom to a ion, which is your electron affinity. Okay. And here is your ionization energy step as well. So it's all the steps we just took. It's just putting it all on one part. Here is your lattice energy. Add them together, we get negative 617. This is showing the same thing for the formation of magnesium oxide as well as sodium fluoride, and it's got all the parts and pieces added in where you have ionization energies, electron affinities, lattice energies. All those steps are going to be the same when you're forming ions, and that's why we can compare them. Now, the formation of ionic solid is extremely exothermic because of the large lattice energy. The ions are packed together so that the attraction between oppositely charged ions is maximized and the repulsion between similarly charged ions is minimized. And that's just the same idea of getting the lowest energy possible and making those atoms happy. Now, for example, if it wanted to find out the delta H formation of lithium bromide, which is essentially what we just did, this is what would have to be given to you. And it would be a matter of just organizing all of that information. It's essentially the same thing we just did, so I'm going to kind of fly through this so I can keep this video a little bit shorter. Just rearranging it, kind of similar to Hess's law, where you got an overall negative exothermic process of 334 kilojoules. And the reason we do this is it allows us to compare certain things and compare substances and which one's more exothermic and releases more energy. And this whole energy piece really drives why reactions and changes actually happen or not, which is a pretty big deal in chemistry. Okay, the next thing that we are going to talk about is partial ionic character of covalent bonds, because we kind of lied to you a little bit last year when we separated it all in different parts and pieces. And percent ionic character, whoops, is just simply the fact that no bond, the reality of it is that no bond is completely 100% ionic bond. Ionic character increases as the difference in electronegativity increases, which remember is your tug of war. And this is just to show you, if you measured the dipole moment, which we're going to come back to a little bit later, and the calculated dipole moment, you can get some comparisons. And so this is just really showing you that your percent ionic character, here are classic ionic, this is our group 1s and our halogen comparisons over here. They're much higher on the, here's your percent ionic character scale, than those are all ionics. And here are your covalents. Okay, so it's just to show you, it's kind of the asterisk that nothing is truly ionic. There's still some electron sharing going on, but we can do some math related to it. And I don't even think I make you do the math, honestly. It's just to be aware of it. Okay, and just as a reminder for ionic compounds, it's anything that's really is greater than 50% on that chart, but excuse me, they will conduct electricity when melted or dissolved. And the reason that it has to be melted or dissolved is so that those electrons can be more mobile. The solids, they just can't work. And polyatomic ions, just as a reminder, contain covalent bonds, but they form ionic bonds with other ions. And we're going to do Lewis structures here in the next couple of units, so that'll make more sense there. Okay, then we got to talk about covalent bonds just a little bit. And we use chemical bonds as a model to describe molecular stability. It's still a model, it's not perfect, and a way to divide up energy released when the molecule is formed. Each bond represents a quantity of energy from the overall energy of a stabilization. It's just a model, it's not perfect. And the way that I think of this, we're going to talk about bond energies here. I think of that covalent bond is the energy that's stored. And that's what we're going to use here to try to look at bond energies. Okay, so for covalent bond energies, and we've seen some of these numbers before, bonds are sensitive to their environment, and the energy does change slightly. So this is just our reminder that when we list bond energy, it's just an average. Okay, so these values that are listed that we will use are just averages, and it's not going to change what we do with them. Okay, the next thing for types of bonds, which again should be a review, single is sharing one pair of electrons. They're the longest in length. Double is sharing 2 pairs of electrons. They're shorter. Triple is sharing 3 pairs of length, 3 pairs, excuse me, and they are the shortest. And we just group the multiple bonds together into the double and triple categories. But again, we learned all this last year, and on a Lewis dot structure, you would see 2 bonds and you would see 3 bonds, and we've seen this with organic as well. This is just some reminders of, here is just the relationship of bond length and bond energy, that the shorter the length, the higher the bond energy, so they kind of have an inverse relationship that we can see with some of those double and triple combinations. This is just some more energies. Just referring you to these are tables that are in your textbook. I'm not totally sure what page they're on, but you may need to refer to some of these in order to do some of the problems in the book especially. And for the energy of bonds, for the bond to be broken, the energy must be added to the system. So it's an endothermic process, and when bonds